Hello, I will be here on behalf of my team. We're 8 students, but today I, team leader Adrian, one of our hardware developers Victor, and one of our software developers Vakas, will present our project. Safe, trustworthy, autonomous delivery system, abbreviated STAD. Let's begin with the problem, railway crossings. Crossings today are the most common place for train collisions and derailment. The current safety for these crossings are railway gates, also known as booms, only installed in about half of crossings in Sweden. However, even in these crossings, there are safety issues. Vehicles and trailers get stuck between the railway gates and thus are a danger to oncoming trains. For vehicles, this is less of a hazard, as the booms are made to be breakable, thus they can drive through them. However, for trailers, they get stuck. There's also a new issue. With the rise of autonomous vehicles, they especially get stuck. The autonomous vehicle will see the boom as an object, a wall, and not allow the driver to drive through, thus putting all passengers at risk. The fears I'm talking about today are not just hypothetical. This year, 2 accidents have happened where trains have collided with trailers stuck between the railway gates. The first one with lethal outcome. The second one avoided lethal outcome because the train conductor was aware of what had transpired during the first accident. The problem is clear. The current safety precautions are insufficient for safety of both train passengers and traffickants on the crossing. A new solution is required. One that would be able to detect whether something is between the railway gate and forward that information to the trains so it can stop in time and thus resolve the situation. So I present our solution. STAD, an autonomous aerial surveillance system, able to use advanced object detection to see whether anything is between the railway gates, transfer this information to a ground vehicle, which has advanced communication capability, able to forward any information to nearby vehicles and trains, thus solving the situation. Let's go through how the system is envisioned to work. Once the railway gates go down, the drone will deploy. It will rise an altitude where it's able to surveil the entire crossing and thus able to detect anything. It will stay in the air for the duration that the booms are down, so that any dangers can be found. If any hazard is found, it will relay the information forward. Once the danger has passed and the booms go up, we will begin the next step of landing, where the drone will go back down onto the ground vehicle, thus concluding the mission. This pattern will repeat throughout the lifetime of the vehicle. In fact, this project is collaboration with 2 other companies in conjunction with MDU, Volvo Construction Equipment and Alstom. Further, it's a combination of their respective projects. From Volvo, a coaxial drone that is powered through a tether. From Alstom, a ground vehicle able to communicate with trains. By doing a hybrid of these projects, we're able to not only handle real-life problems, but also further the goals of our stakeholders. I will now leave the stage to Victor, who will talk more about the drone and the hardware of our product.
So initially we had a few requirements from our stakeholders. These requirements were long flight duration for the drone. This is because if there's a delay for the train, the drone can finish the mission without having to land and recharge. So it should be able to keep up in the air for a long time. Then another requirement was that the drone should be tethered. This also helps with the drone's mission time, but it also suits the drone for Swedish flying regulations. Then the drone has to be able to identify and classify hazards. So we equip the drone with a camera module in order to look down upon the area of interest. And obviously we want to maximize efficiency for the drone. It shouldn't consume too much power when it's running. And the final requirement is that the drone should have wireless communication. So what's a coaxial drone really? It's kind of like a helicopter, but without the tail rotor. So the benefit of a coaxial drone as compared to a regular single copter is it has torque neutralization. This is due to the fact that we introduce a second propeller that rotates in the opposite direction of the first propeller. This cancels out the torque coming from the first rotor. And a coaxial drone also has some stability benefits because we're keeping the center of mass below the pivot point of the drone. This design also goes naturally with a tether design. So the tether is pulling on the lower part of the drone. And coaxial drones are usually more efficient than single copters because of the fact that we're removing the tail rotor. We can spend more of our power and energy towards thrust. So how are we controlling our coaxial drone? It's controlled by tilting the head of the drone in a desired direction. And this is done by tilting two servo motors, one in either X and Y axis. Then our drone is not the only part of our system. We also have a smart winch. This consists of a spool and a guiding system that guides the cable along the spool. And then we have a stepper motor, receives information from the desired height of the drone, and it calculates how much cable it's supposed to give. Then the final part of the winch system is the landing platform, which the drone just comes down and lands upon. Our ground vehicle has two separate power systems. It's one for driving the PX2, and the other power system is to drive the motor. And the ground vehicle is performing the bulk of all the computing in the system, along with all the signal processing and the classification. And some challenges that we met during this process were code dependencies in between the motor dimensioning, increasing the current of the drone, which in turn increased the thickness of the cable, which in turn increased the weight. So we had to decide dimension pretty well. Another problem was that we never actually got the equipment required for the test rig, so we were never able to try this drone in a real application, sadly. And this is just a proof of concept, so there are a lot of optimizations to be done on the system as a whole. And now I will leave the word to Vakas, a software developer in our team.
Thank you. So coming to the interesting part, so our software system is divided into two parts. First one is the drone and the other one is the ground vehicle. So the drone has a flight controller which has the telemetry information about the drone. For example, where the drone is currently, and then we have a Raspberry Pi with it. Raspberry Pi take this information from the flight controller. Along with it, it also takes images from the camera modules and send it to our ground vehicle. So our ground vehicle has this computer called PX2. It does its AI and all computation and send it back to the drone system so the drone can decide how much it has to move and in which direction. So for our simulation, we have used Gazebo. It has a word and agents. The agents basically interact with the words. So in this environment, you can decide how many motors the drone has, where these motors are situated, and how much thrust these motors produce. It also works really well with the Q ground controller. It is basically a tool which we can use for configuring the drone remotely. For example, if something goes wrong and we have to configure the drone, we don't have to connect it to a computer. We can just do it remotely. So the takeoff system and landing system. The takeoff system is comparatively easier because you don't do a lot of computation. You just provide some PID values and the flight controller take care of it. But the landing system is a bit tricky. We are using Aruku markers for it. These are sort of QR codes, but a little bit different. They keep the information of the location. So the way our landing system works is our drone takes off. It identifies a Aruku marker on the landing pad, calculates its position from the Aruku marker, and then we apply PID controller to it, so it tells us how much action needs to be taken and in which direction. Another CPU intensive processor or AI models. The first one we are using is OpenCV for identifying our region of interest, which is the railway crossing area. How we are doing it, we are placing 4 markers around our region of interest, and our OpenCV system finds it and draw a rectangle on it. Even if one of the marker is missing, we can still predict it by placing 4 markers diagonally of different sizes. We are also using YOLO, which is a machine learning model, to identify any hazardous objects. So in our study, we are just considering animal, people, and vehicle. The way our system works is if the drone takes off, it identifies an object and also find its location. If its location overlaps with the location of our region of interest, it generates an alert and sends that alerts to a ROS topic. So that alert can be later used by the train systems to take any avoidance actions. After this, we have a little bit demo of our system. I hope you guys can see it. Yeah, so the drone takes off. We have fastened a little bit because the landing system is taking like up to 45 seconds, but it finds the marker after 45 seconds. And now it has found the marker. Within 10 inches of the marker, it lands. So we would like to reduce this time by like 20 seconds, and it is possible, yeah, with given time. So after our simulation, I will hand into Adrian to talk about the results in our future work. Thank you.
Yes. So what have we achieved? Well, we've been able to build the drone as well as the winch and set up both the simulation and software and integrate it all into one package. However, as mentioned earlier, we were never able to get test rig. So we're actually never able to do real-world testing with the drone. However, earlier testing shows that the drone has enough power to lift, but we have not been able to test the control itself. That is something we would leave to future work, the next iteration of the project. For the test rig, as well as optimize the drone body design. During the design process, we found a lot of optimizations. Specifically, the drone could be made a bit smaller, thus lighter and able to work with smaller motors. Also, the current train communication is made as an interface, as the full communication capability is not developed today. And the current system we have is made to be easily integrated when future developments are made. That's all for us. I'd like to say if you have any questions, please feel free to ask them in the demonstration booth next to us after the presentation. And I thank you for listening.